Hello, and welcome to the science of sleep, where the floorboards of the universe creak softly beneath your feet and curiosity hums quietly in the dark. Tonight, you don't need to hold on to anything, not ideas, not expectations, not even gravity, because even that is up for debate. Just breathe. Let your weight drift away, as if the world beneath your bed is made of shimmering possibilities, because in a way, it is. You've spent your day in a world that feels certain. Keys stay where you leave them. Toast doesn't quantum tunnel through the table. Socks don't vanish into alternate dimensions, at least not visibly. But beneath this heavy quilt of reality is a strange and jittery fabric, stitched together with rules that feel more like riddles. You live in a universe where things exist and don't, where particles only make up their minds when someone's watching, where the deeper you look, the fuzzier things become. And still, your morning coffee doesn't spontaneously teleport to the ceiling. So strange. You might be wondering, why doesn't the bizarre behavior of particles, those tiny flickers of uncertainty, spill out into the world we touch and smell and drop our phones into? If the universe is quantum at its core, why do you feel so solid? To answer that, you have to start small, very small. Imagine a particle, maybe an electron, just sitting alone in a vacuum. Or better yet, not sitting, because sitting implies location. And electrons, you'll soon realize, don't much care for being anywhere in particular. This electron doesn't have a specific position. It's more like a soft whisper stretched across space, a suggestion, a probability. Now, zoom out, drift out, slowly. That tiny flicker is part of an atom, which becomes part of a molecule, which binds with trillions of others, building up the familiar coffee mugs, cats, dreams, bills, you. But somewhere in that drift, something changes. The quiet shimmering of probabilities begins to settle. The fuzz becomes focus. Quantum turns classical. And no one quite knows exactly when or how that shift becomes irreversible. But let's go back. You are floating just above a dark, frozen vacuum, a silence broken only by the flickering heartbeat of virtual particles blinking in and out of existence. A single electron is your guide. It doesn't move through space the way a pebble does. It spreads. It drifts like perfume from a bottle shattered in slow motion. Where it will be found isn't where it is because it isn't yet. Down here, the universe doesn't commit. This strange looseness, this non-committal fuzziness, is the foundation of everything. And it's not just electrons, photons, protons, neutrinos. They all play this shadow game. They all follow rules written not in certainty, but in probability. A roll of a die with infinite sides. Now here's where things get spooky. These particles, they don't like being looked at. The moment you try to measure their position, bam, the wave collapses. It picks a spot. Like a teenager caught doing something embarrassing, it suddenly stands still and says, "What? I've been here the whole time." But you know better. A moment ago, it was nowhere, or everywhere. This oddity, called wave function collapse, is a big deal, because it means particles don't have defined properties until they're measured, until something interferes. But that's just the beginning. You might wonder, okay, weird stuff happens to particles. But what if you had two particles? Now you're in even stranger territory. Because sometimes particles get entangled, linked in such a way that one instantly knows what the other is doing, even if they're light years apart, like cosmic twins finishing each other's quantum sentences, which sounds romantic, until you ask why your shoes never entangle with each other across the closet. It's like the universe has a secret club for particles, and the big stuff, mugs, socks, flamingos, isn't invited. That's the heart of tonight's question. If quantum rules run the universe, why doesn't reality shimmer like a dream? Why do you wake up in the same bed you fell asleep in? Why don't spoons teleport? Or apples hover? Or pass through walls like lonely ghosts? The answer, or at least part of it, is this. They could, technically, but they don't. Not because they're forbidden, but because the odds are absurdly low. Like flipping a coin and getting heads 1 trillion times in a row while riding a unicycle on Mars, blindfolded during a meteor shower. Quantum effects can happen to big things. They just don't want to. So you live in a world where the weirdness is still there, whispering underneath. But it's muffled, like a dream you forgot as soon as you opened your eyes. Still, every now and then, in laboratories colder than Antarctica, in machines quieter than space, scientists do coax those whispers back. They cool objects to near absolute zero, shield them from noise, from light, from time itself, trying to catch quantum behavior in things you can see. And sometimes it works. A speck of dust, briefly, behaves like a particle and a wave, just long enough to remind us that under the surface, nothing is truly still. So tonight, as your body softens into sleep and your breath slows, remember this. You are floating on a sea of probabilities. You are made from things that don't quite exist until they're observed. You are composed of quiet rules, playing out beneath the surface of certainty. And in that silence, you might find peace, or at least a moment to let go of needing the world to always make sense. Because it doesn't. Not really. And yet your pillow remains beneath your head. Your room stays where it is, and you are exactly where you need to be. Even if, technically, you could be somewhere else entirely, you drift further now, deeper into that trembling silence beneath reality, where particles don't walk, they shimmer, where position is not a dot but a blur, a suggestion, a maybe. Let's follow one of them again, shall we? Tonight's guide is an electron, and no offense to it, but it's not particularly special. Electrons are everywhere, in your fingernails, in moonlight, in leftover birthday balloons. But this one, for now, is alone, isolated, free from disturbance, like a meditating monk in an abandoned mountain temple. Now imagine releasing it. What happens next is not a motion you're used to. It doesn't tumble forward like a pebble or streak like a comet. Instead, it becomes a wave, a probability wave. And here's the twist. It's not waving through space, like water or sound. The electron is the wave. That's not a metaphor. That is the reality. This is called wave-particle duality, and it's not just for electrons. All matter behaves this way. Yes, even you. It's just that for big things like people, cats, or pancakes, the wave part is incredibly tight. So tight it's practically non-existent, like trying to notice the wobble of a skyscraper during a breeze. It's there, but you'd need a microscope the size of Jupiter to care. But our tiny electron? It spreads wide, like a ripple on a pond. And until something measures it, until it's asked, "Hey, where are you exactly?" it doesn't answer. It doesn't have to. In fact, the only honest thing to say is, the electron is everywhere the wave says it could be. This is unsettling at first. You want particles to be polite, to choose a side, but in the quantum world, asking a particle to commit is like asking a cloud to become a brick. Now here's something to make your eyebrows levitate. In 1924, a physicist named Louis de Broglie suggested that all matter has a wavelength. He proposed that particles like electrons should also act like waves. And sure enough, when people looked, they found exactly that. Shoot electrons at a barrier with two slits in it, and they'll form a ripple pattern on the other side. The kind of pattern you'd expect from waves crashing through a fence, not little bullets. So what gives? It's not that the electron goes through one slit or the other. It goes through both at once, like it splits itself into ghost versions and interferes with itself on the other side, just like a water wave would. And if that sounds like it should belong in a sci-fi film starring a confused toaster, well, welcome to quantum physics. You'd think that's the weirdest part, but no. The true punchline comes when you decide to peek, place a detector by the slits just to see which path the electron takes, and poof, the ripple pattern vanishes. Now the electron behaves like a boring little pellet. One slit, one path. Predictable. So it was acting like a wave until you looked? Exactly. Just your act of measuring changes reality. The universe plays coy. It doesn't just hide the answer, it rewrites the question. And this isn't just a parlor trick, it's a fundamental truth. Electrons, photons, atoms, all can behave like waves, and do when left unbothered. It's only when something An observer, an interaction, a stray photon collapses that shimmering mabeness into a concrete there it is, which raises an uncomfortable question. If tiny things can be waves, and are waves, what stops that from scaling up? Why doesn't your cat blur into all possible corners of the kitchen? Why don't you, as you walk half asleep into the fridge at 2 a.m., suddenly interfere with yourself? The answer is sneaky, and you've already brushed up against it. The larger the object, the shorter its wavelength. Your body is made of particles with such vanishingly small wavelengths, their quantum waves are squashed into invisibility, like trying to measure the thickness of a shadow. But more importantly, it's not just about size, it's about isolation. Your poor electron was alone, isolated, zen, but you are a carnival of chaos, constantly interacting with air, light, heat, noise, memory, thought. Every nanosecond of your existence is a collision, and each one of those interactions measures you, not with instruments or scientists, but with reality itself. Every breath, every breeze, every vibrating atom around you is, in a way, observing you. So your wave function, it collapses instantly, over and over, without you ever knowing. You're not even given the option to act quantum. And that's okay, because it's exhausting to be uncertain, to be everywhere, to not know who you are until someone else defines you. You've lived that in high school. You don't need to live it again on a subatomic level. Still, sometimes you might wish you could access that shimmering softness, that looseness, the ability to be many things at once, not trapped in one state or one outcome. That's the real poetry of particles. They remind you that at the root of being, there is potential, possibility, a refusal to collapse until the very last moment. And perhaps that's something to hold on to, not with your hands, but with your breath, with your imagination, as you fall deeper into sleep. You are not a wave, but you came from one. And maybe, just maybe, some part of you still remembers how to shimmer. You're still gliding gently through this underworld of physics, part dream, part code, when something ahead catches your eye. It looks simple enough. A wall, painted in soft shadows, with two narrow slits cut into it. You recognize it right away. The double-slit experiment, a classic. It's been around for over 2 centuries, but it still feels like a prank the universe is playing on us. Let's walk through it slowly, no rush. Your mind is already quiet. And in this state of calm, you might notice something everyone else tends to miss. This experiment is not about science. It's about reality itself misbehaving when no one's watching. Imagine you have a cannon one that fires tiny particles instead of cannonballs. You aim it at a wall with 2 slits. On the far side, there's a blank screen that lights up wherever a particle hits. Nothing fancy. Just a particle gun, 2 slits, and a wall. First, you fire a stream of particles, say, electrons. You expect them to go through one slit or the other, like pebbles through a doorway, and you expect them to pile up behind each slit in 2 neat matching clusters. But that's not what happens. The electrons land in a complex pattern of alternating light and dark bands, a pattern not made by particles, but by waves. They interfere with each other, peaks and troughs, cancelling and amplifying, just like water ripples overlapping in a pond. But wait, each electron was fired, one at a time. There was no other particle around to interfere with. So, what exactly interfered with what? The only possible answer is a little absurd. Each electron interfered with itself. It went through both slits at once. It was in 2 places, or rather, 2 possibilities at once, until you try to catch it in the act. Now you place a detector by the slits just to see which one the electron actually passes through. Maybe you don't trust it. Maybe you want to prove it chooses. But the moment you add that detector, the pattern on the screen changes completely. The interference vanishes. The ripples collapse. Now the electrons land in 2 boring piles, just as you'd expect from pebbles. By looking, you've changed the outcome. Reality, whatever that word means, depends on whether it's being observed. It's like trying to watch someone dance alone in a room, only to find they freeze the moment you open the door, close it, and the music resumes. And that's weird, almost offensive. You've grown up thinking of the world as existing independently of your awareness, that the moon is there whether you look or not, that coffee stays hot whether or not you check. But the double slit experiment whispers otherwise. The observer you, or your instrument, or even a passing photon plays a role in deciding which version of reality becomes real. This isn't metaphor, it's physics, tested, repeated, confirmed. Now lean back a little. Let the image fade. The wall, the slits, the screen, all disappear into velvet dark. What lingers is the idea, the suggestion that deep below the surface of your waking life is a system that doesn't decide until it has to. A world of infinite maybes, collapsing into one solid yes, only when the curtain rises. It's unsettling, sure, but also beautiful, because it means that observation isn't passive, it's creative. When you look, you're not just seeing, you're participating. In a sense, you are part of the equation. Now, don't worry. You're not waking up tomorrow with a quantum superpower. You're not going to blink your cereal into multiple timelines. This effect lives in the smallest corners of reality, where particles dance on the edge of uncertainty. But the implication lingers. When no one looks, the world isn't pinned down. It's a swell of probabilities. The moment you turn your attention toward it, poof, it commits to something. A decision is made. And maybe that's not just physics. Maybe it's a little bit like life. You never know what version of yourself exists until you choose, until you look, until you act. You can be brave and shy, angry and tender, joyful and uncertain, all potentialities, all real in their own soft shimmer. But at some point, you step through the slit. You collapse your own wave function. And that's what people see. So here you are, lying in your bed, listening to these ghostly laws, and your brain might be asking, is the whole universe undecided without me? Not exactly. The universe has its own rhythm. You don't control it. But you're also not a bystander. You are entangled in its structure, part of its fabric, a ripple within it. Even now, your awareness, your breath, your presence sits like a lens on top of the cosmos, tilting probabilities into paths. Maybe you've never thought of yourself that way. As someone whose presence matters not just emotionally, but physically, whose noticing nudges the world into place. But maybe you should. Maybe that's the lesson in all this weirdness. That in the smallest experiments, performed with isolated particles and absurd detectors, lies a truth that echoes back up to your very life. The world changes when you pay attention. So take another breath. Let your eyelids hang heavy. You don't need to understand everything right now. You just need to drift and let the universe shimmer behind your closed eyes, uncollapsed, unhurried, unobserved. You're still floating, and somewhere behind you, the slits have vanished. The wall is gone. The screen is blank. What's left now is the sensation that something watched was forced to behave. Something unknowable was made solid, just because you peaked. But what happens at that moment of peaking? What really happens when a quantum wave function collapses? You're about to find out. And it won't be dramatic. There are no symbols, no cosmic drum roll, just a soft hush, like the universe holding its breath. Imagine you're in a room with a sleeping cat. You hear it purring faintly. You don't know whether it's on the couch, under the table, or curled beside the bookshelf. You imagine it in each of those spots, purring somewhere, possibly everywhere. But the moment you flip on the light, you find it in one place. That's wave function collapse. Before measurement, a particle exists in a state called superposition, a blend of all the possibilities. It's not indecisive. It simply doesn't have to decide yet. Reality doesn't ask it to. But when you observe it, measure it, something changes. All the possibilities vanish but one. The wave function, this complex mathematical ghost that described all potential realities, snaps into a single outcome. It's like choosing a page in a choose-your-own-adventure book and watching all the other endings dissolve. The question, of course, is why? Why does observing collapse the wave function? No one truly knows. There are theories, yes, some elegant, some a little drunk, but we're still left with this strange event. The moment something interacts with a quantum system, be it a detector, a molecule, a wandering beam of light, the shimmering cloud of possibilities shrinks into one. Reality gets stage fright. And this isn't just metaphor. There are real experiments showing this collapse happening in real time, devices carefully built to watch the moment when a particle shifts from possibility into presence. It's not a violent crash, not a spark of drama. It's subtle, soft, almost sad, as if the particle had 1,000 lives, and you asked it to choose only one. Now drift for a moment into a stranger place. Imagine this. You don't observe the particle directly, but you know which path it took, not by looking at it, but by measuring something else it touched. Guess what? The interference vanishes anyway. Knowing, even indirectly, is enough to collapse the wave function. It's not the eye that matters, it's the information. The universe doesn't need eyeballs, it needs entanglement, measurement, interaction. In that sense, reality is like a gossip. It doesn't need to see the thing itself, it just needs someone, somewhere, to know. Which raises another question. Who or what counts as an observer? Is it just humans? Is it cameras? Is it electrons themselves, bumping into each other? The uncomfortable answer is, we don't know. We don't have a clean answer for when or how the collapse happens, or whether it's real at all. Some physicists argue that collapse isn't a thing, that the wave function doesn't truly collapse. We just act like it does because we're inside the system, not outside watching from a cosmic balcony. It's kind of like watching someone make a choice in slow motion. You can't see the brain's chaos. You only see the final result. The coin lands, the footsteps, the cat jumps. And maybe the universe is the same. Maybe wave function collapse is not the destruction of options, but just your limited view zooming into one slice. Still, it feels deeply personal, doesn't it? The idea that reality remains undefined until it's poked, until some fragile thing triggers the collapse. It's as if the universe is waiting to see which version of itself it should be, like a shy artist behind a curtain. And that shy artist is everywhere. Collapse happens constantly. Zillions of particles every second, flitting into certainty, not just in labs, but in your coffee, your socks, your neurons, your breath. The quiet ballet of measurement plays out endlessly each moment, another curtain drawn. And while that might sound overwhelming, it's actually the reason why things stay put, why your hand doesn't teleport, why your fridge doesn't flicker, why your thoughts have continuity. The constant collapse locks in the structure of your world. Without it, everything would be fuzzy, unstable, like a dream you're not quite inside of. So here's a thought to carry into sleep. You live in a reality stitched together by billions of collapsing wave functions. Every breath, every tick of the clock, every atom you bump into each one, a silent agreement between possibility and presence. And maybe that's what consciousness is, too. Maybe you're not just observing the world. Maybe your awareness is a kind of collapse, a spotlight that turns probability into presence. What a strange power to have, to bring things into focus simply by being, not by effort, not by will, just by being. And as your eyes flutter slower and the edge of sleep creeps in like fog, let yourself shimmer for a moment between states, between possibilities. You are not fixed, not yet, but soon, gently, you will collapse into rest. Somewhere behind you now, the wave function has collapsed. The possibilities have quieted, and what remains is definite, settled, predictable. But the question still floats beside you like a ghost. Why doesn't the weirdness stay? Why do we only glimpse it in secret, quiet corners of the universe, and never in the warmth of a kitchen or the chaos of a birthday party? You might be tempted to say it's about size, but that's only part of the answer. What really matters is noise. Let's talk about decoherence. Don't worry, it's not as grim as it sounds. It doesn't mean the universe is breaking up with you. It's more like reality is turning the music down, smoothing out the shimmer, sanding down the rough edges of quantum magic until all that's left is the familiar. Imagine you're holding a tuning fork in a soundproof room. You strike it clear, ringing, pure. The tone fills the space like light. Now imagine opening the door and walking into a stadium full of drummers. That elegant tone gets drowned. It's not gone, it's just lost in the noise. That's decoherence. It's what happens when a delicate quantum system, something like a particle in superposition, touches the messy, noisy world around it. Because out here, in the macroscopic realm, nothing is ever truly alone. Everything is touching everything else all the time. Molecules jostle, photons strike, heat wiggles its way through the cracks. The quiet wave function, once free and fluid, is now surrounded by chatter, and it folds. It loses its shimmer. It decoheres. That's why you don't see cats in two places at once. Not because the laws of physics forbid it, but because the environment ruins the illusion before you even have a chance to look. It's not about size. It's about isolation. Tiny things, like electrons or atoms, can be kept isolated, placed in cold, quiet, carefully designed laboratories. There, they're shielded from the blaring orchestra of the everyday world. That's when the magic can happen. Interference, superposition, entanglement. But the moment those same particles are allowed to bump into other particles, the quantum spell breaks. And that's decoherence in action. The environment becomes an accidental observer. Every molecule, every vibration, is like a nosy neighbor peeking through the curtains, collapsing your quantum privacy into classical certainty. You might think, well, why can't we just block everything out? And we try. Oh, how we try. Quantum physicists spend lifetimes building systems to isolate particles. They chill them to near absolute zero. They vacuum out every stray atom. They encase them in elaborate fields to block light, air, thought, and even then, it's a race against time. Decoherence creeps in like fog under the door, because the world doesn't like secrets. The moment something quantum brushes against the environment, poof, it becomes classical. Let's make that more vivid. Picture a ballerina dancing on a frozen lake under starlight. She's graceful, alone. Her movements defy gravity, spins so delicate they blur into air. Now, drop a single snowflake on the lake, then another, then a gust of wind, then footsteps from curious onlookers. Soon the ice cracks, the reflections smear, the ballet is over. That's decoherence. The world intrudes, not with malice, but with sheer, overwhelming presence. But don't be sad. This is not a tragedy. Decoherence is also what gives you a stable world, a world where chairs don't flicker and toast stays put, a world where memory can form and planets don't split into multiple versions of themselves mid-orbit. You live in a post-decoherence universe, a realm where the shimmering rules of the quantum world have been translated, through relentless interaction, into the sturdy reality you recognize. And that's kind of beautiful. It means that stability isn't an accident. It's something earned, something that emerges from a storm of collapsed possibilities. Your life, your thoughts, your heartbeat are all consequences of decoherence doing its quiet work. There's even a theory called quantum Darwinism that suggests this process is like evolution. The quantum states that survive are the ones that can imprint themselves onto the environment the most robustly. Reality, in this view, is a selection of what can be shared, copied, and stabilized across space and time. So when you touch a doorknob, you're not just touching matter, you're interacting with a vast history of stabilized outcomes, things that have won the battle against decoherence. That's why quantum weirdness doesn't walk around in your living room, not because it's forbidden, but because it's buried, smoothed, silenced. And yet, it's still there, always, behind the noise, beneath the stability, within the quietest moments of the smallest things. The shimmer never fully disappears, it just waits, like a note held in silence, like a possibility suspended until the world stops paying attention. So tonight, as your breathing slows, as the edges of your world begin to blur, let that shimmer drift back in for a moment. Let yourself remember that beneath the ordinary is something extraordinary. You are not separate from it. You are built from it. And though decoherence has quieted the dancer is still within you, still spinning. The silence holds steady now. A kind of trust has formed between you and the universe, unspoken, soft. You've learned its secret, that the strange quantum shimmer is always there, even when the lights are on. So let's drift into something even stranger. Imagine two particles, maybe photons, maybe electrons, born together in the same breath of energy. You separate them. One stays here, the other floats off across the lab, across the country, across the galaxy. And yet, somehow, they still know about each other. This is entanglement, one of the strangest, most delicate phenomena in physics. When two particles become entangled, their states are linked. If one spins left, the other spins right. If one is measured as up, the other must be down. No matter the distance, no matter the silence between them. Einstein hated it. He called it spooky action at a distance, because it seemed to break everything he believed about space, about causality, about information needing time to travel. But experiment after experiment has shown it's real, unsettlingly real. If you measure one particle's state, the other's collapses instantly, as if the universe is whispering, they are not two things, but one. You might be thinking, that's wild. Can we entangle anything? Like my toaster and my car keys? Not kite. Entanglement is a delicate thing. It requires perfect preparation, a clean environment, a kind of cosmic intimacy. The moment an entangled particle interacts with something else, poof, it decoheres, just like you learned before. The connection breaks, the thread snaps. And that's the heart of our question tonight. If quantum weirdness is real and entanglement is the deepest weirdness of them all, why don't we see it in everyday life? Why aren't you entangled? And the short answer is, you probably were, once. Somewhere in the early moments after the Big Bang, particles flew apart in patterns that may still be entangled today. Some theories suggest the whole universe began in an entangled state, one enormous, synchronized wave function, and maybe parts of that are still echoing through you, through starlight, through old photons crawling across time. But here's the thing, entanglement doesn't scale well. Let's say you try to entangle two small diamonds. It's been done, but just barely. Scientists isolate them in quiet chambers, chill them to near absolute zero, and listen for the faintest signs of quantum correlation. Now imagine trying that with, say, a shoe. Shoes are messy. Their atoms are bouncing around, touching air molecules, absorbing heat, and radiating tiny photons like sweaty quantum radiators. There's no way to keep them isolated long enough. Every tiny interaction is like an accidental observation, ruining the entanglement before it even starts. You can't entangle a shoe because the world keeps interrupting. It's like trying to whisper a secret to someone across a crowded stadium. Every other noise drowns you out. And here's a weirder thought. You, right now, are made of countless particles, electrons, quarks, protons, all bouncing, interacting, decohering. Even if they were entangled once, that connection was scrambled long ago. Not lost, just unreadable, as if the thread was tangled in so many knots you can no longer follow it. But again, that's not a failure. That's how your body exists. That's why your thoughts aren't smudged across realities. That's how your feet stay on the ground. Entanglement, after all, isn't about being stuck together. It's about correlation without communication. You don't send a signal from one particle to the other. You simply know that their fates are joined, no matter the gap. If that sounds poetic, good, because it is. It means that connection is more fundamental than distance. That two things can be part of one state, even when they appear separate. That wholeness can exist beneath division. And maybe that's not just quantum philosophy. Maybe that's something to carry in your own life. That when you love someone, really love them, there's a kind of entanglement. Not mystical, not measurable, but real. A link that persists across time and space. You feel it in the tug when they're far away. In the ache when they're in pain. In the silence that still feels full. Maybe the quantum world is just reminding us of something we already knew. That things, people, particles, memories are never as separate as they seem. Still, don't expect your furniture to teleport anytime soon. Macroscopic objects, tables, books, burritos are too messy to maintain that kind of connection. Their atoms bump and jostle and smear any lingering entanglement into oblivion. But researchers are trying. There are experiments where tiny objects, mechanical resonators, superconducting circuits have been entangled, It's difficult and fleeting and beautiful, like catching lightning in a bottle, or a dream in a whisper. Someday, we may find a way to preserve entanglement in larger systems, perhaps even use it to send unbreakable messages, to build quantum computers, to map the brain in ways we haven't imagined. But for now, let the strangeness be enough. You are here, lying still, in a body made from atoms that once danced in synchrony with the stars, particles that spun beside others in the quiet before light. You've forgotten those connections, but the universe hasn't. They're still there, somewhere in the background, faint as a memory, strong as truth. And maybe that's why you sometimes feel a pull you can't explain, a warmth with no source, a presence, even when you're alone. Not spooky, just connected. As always, somewhere between wakefulness and dream, you feel yourself suspended not exactly here, not exactly there. That's the perfect place to talk about something quantum particles know all too well. Superposition. It's the heart of the mystery, the most quietly rebellious idea in all of physics. And yet, it's not hard to grasp. In fact, you've felt it before when you're between decisions, when a thought isn't yet formed, when a feeling hovers before becoming joy or sadness. That suspended in-betweenness. That's the human version of superposition. For a particle, though, it's literal. A single photon can take two paths at once. An electron can be in multiple energy states. An atom can spin both clockwise and counterclockwise. Not in a fuzzy, metaphorical way, but in a precise mathematical one. When left unmeasured, these particles occupy all their possible states simultaneously. They're not choosing between A or B. They are A and B and C and Z. Until someone asks, then the wave function collapses and the particle chooses. Just one. Now, let's take a leap. Imagine you could do this. Be multiple versions of yourself at once. In one world, you took the job. In another, you stayed home. In one, you said yes. In another, not yet. All those versions still humming just below the surface possibilities you never quite lived. And that's what makes superposition so haunting. Not because it's weird, but because it's familiar. You live surrounded by unlived lives, not as regret, but as richness. Quantum particles remind you, reality is not a narrow path. It's a shimmering field of options. What you see is just one sliver, frozen by interaction, chosen by collapse. But in the deep structure of the universe, there's always more. Let's return to the lab for a moment. You take an atom and cool it to nearly absolute zero, so cold that it stops jiggling. Now it's possible to prepare that atom in a superposition of two energy levels, not switching back and forth, truly occupying both at once. And what happens next? You run an experiment called an interference test, and the results only make sense if the atom really did live in both states. Superposition isn't hypothetical, it leaves fingerprints. You might expect that this trick only works for atoms, but physicists have done it with molecules too, some containing dozens of atoms. They've sent them flying through vacuum chambers and seen them interfere with themselves. That's superposition on a scale you could almost see. So why can't you flip a coin and have it land on both heads and tails? Because of the same familiar enemy, decoherence. Superposition is delicate. It hates being watched. The moment a system interacts with the environment even lightly, it gets nudged into choosing. A photon, a gust of heat, a whiff of air, that's all it takes to ruin the quantum ambiguity. And big objects? They're never alone. You are a walking billboard of interaction, sweating, breathing, radiating infrared light, brushing against a billion particles with every step. There is no space in your life quiet enough for superposition to survive. That's why you don't shimmer. But the truth is, your particles still could. In the right conditions, cooled, isolated, suspended tiny systems can be coaxed into superposition even today. In labs across the world, physicists are balancing particles on the edge of multiple realities. And in those fragile moments, reality is unfinished, uncommitted. You might ask, what does this mean for free will, for choice? It's tempting to draw conclusions, that maybe we are more quantum than we admit. That possibility isn't just physics, it's philosophy. That even if your body isn't in superposition, your life sometimes feels like it is. We don't often speak in those terms. We prefer clarity, finality. But how many times have you lived in between? In between relationships, in between jobs, in between yes and no. Not collapsed, not settled, suspended. That is superposition of the soul. And maybe it's not something to fear. Maybe it's a gift that you are allowed to linger in the maybes. That choice doesn't always have to be immediate. That truth can be pending. The quantum world has no problem with that. So maybe you don't have to either. Here's something else. Superposition isn't limited to location or spin or energy. It can involve entire histories. There are quantum models of the universe where the past itself is fuzzy until measured. Not just the future, the past. That is, until you make a present observation, the path that led to this moment remains uncertain. Reality isn't a line. It's a braid of possibilities, tugged into shape only by your attention. Think of it like a painting slowly revealing itself, not stroke by stroke, but depending on where you're standing, depending on what you notice. You're not just witnessing the world, you're helping define it. And that's not exaggeration. It's the logical extension of quantum rules into the strange corners of experience. Some interpretations suggest the universe doesn't choose a story until a choice has to be made. So tonight, as you fall asleep, ask yourself, what stories of yourself haven't collapsed yet? What parts of you are still shimmering, unmeasured, possible? You don't need to answer. Just know, the moment of collapse can wait. For now, you are allowed to be in between, both here and elsewhere, both you and more than you. And in the soft dark, where the rules loosen their grip, you shimmer like a quiet truth still waiting to be told. You're nearly asleep now, breathing slow, barely tethered to this world, which is perfect, because the next image is going to feel like something out of a surreal bedtime cartoon. Let's open the box. You know the one? It's famous. It has a cat in it. Schrodinger's cat. The thought experiment is almost a cliche by now, but tonight, let's walk through it slowly, thoughtfully. Let's feel what it's really asking. Picture it. A closed box sits in front of you. Inside is a cat. Also inside, a tiny bit of radioactive material, a Geiger counter, a vial of poison, and a hammer suspended like some cartoon trap. Here's the setup. If the radioactive material decays a totally random quantum event, the Geiger counter detects it, the hammer drops, the vial breaks, and the cat, well, you get the picture. But until you open the box, until you look inside, quantum mechanics says the decay is in superposition. It has both happened and not happened, which means somehow, unbelievably, the cat is both dead and alive. Simultaneously, you might laugh, or grimace, or say, that's not how cats work. And you'd be right, because Schrödinger never meant this to be taken literally. He was actually making fun of quantum theory. He wanted to point out how absurd the implications were if we extended quantum rules into the macroscopic world, into living things, into fur and whiskers and purring and paws. But the joke took on a life of its own, and now, people everywhere picture this poor quantum feline trapped in a box, both gone and not gone, waiting for someone to look and decide its fate. But here's the real lesson. The cat isn't what matters. It's the boundary. The edge where quantum weirdness ends and classical reality begins. Where does the superposition stop? At the particle? At the Geiger counter? At the cat? At your eye? Your brain? No one really knows. And that is the point. Because somewhere along that chain from radioactive decay to paw print to person opening the lid, superposition collapses. But where exactly? And why there? This is called the measurement problem. And it's not just a philosophical puzzle. It's a scientific mystery. We don't have a firm answer. The cat in the box forces us to ask, why does the quantum world behave differently when scaled up? What's stopping us from seeing multiple realities in our own living rooms? Why don't squirrels phase in and out of existence? Why don't you find your socks in 2 drawers at once? Why aren't real cats quantum? Because, As you've learned, the more a system interacts with its environment, the faster it decoheres. A cat is made of trillions of particles, constantly interacting with air, fur, sound, breath. Even inside the box, it's not isolated. In reality, the cat's quantum state collapses almost instantly long before you ever open the box. So the alive and dead superposition, it's already resolved. You just don't know the answer yet. That's important. There's a difference between something being uncertain and something being undecided. Quantum systems can exist in genuine undecidedness, but macroscopic objects, like cats, or you are more often just unknown until observed. The box doesn't hold a paradox, it holds a secret. But for a flicker of a moment, before the first photon bounces, before the air wiggles, before the molecules conspire, maybe, just maybe, that cat flutters between two worlds. And that's what keeps physicists awake at night. Not the cat, but the curtain, the veil between the microscopic and the macroscopic, between quantum and classical, the boundary where maybe becomes is. Is that boundary sharp? Or is it fuzzy? Can we shift it? Push it? Some scientists think we can. They build ever larger systems and push them into quantum states. Superposition has already been demonstrated in molecules, small mechanical devices, and even tiny sheets of metal, a whisper away from visibility. If we keep going, could we build a Schrodinger's cat that actually stays in superposition long enough to observe it? Not the cat itself, but a proxy. A system large enough to see with your own eyes the shimmer between two outcomes? Maybe, but it would take silence, cold, isolation so deep it's almost sacred, because anything can break the spell, even the light from your own gaze. So for now, the cat remains a thought, a story, a boundary line we draw in our heads to mark where logic starts to fray. Still, it makes you wonder, doesn't it? How much of your own life is like that box? Moments you haven't looked at yet, decisions you haven't opened, feelings you've sealed away, waiting for the courage or the quiet to lift the lid. And inside, two versions of you, one that moved on, one that didn't, one that forgave, one that still waits. Both possible, both alive, in their own way, until you choose to look. And maybe that's the deeper metaphor, that we all carry boxes and cats and quantum memories of unlived lives. So tonight, don't be afraid to let them stay closed. Let the possibilities breathe. Let the cat purr or not unmeasured. Let your life be uncollapsed for one more breath. You don't need to know everything. You just need to sleep. You're somewhere between dreaming and dissolving now, curled like a comma on the edge of consciousness. Which is fitting because this part of the story is all about temperature and the strange way it decides who gets to shimmer and who must sit still. Let's start with a truth so simple it's easy to forget. Heat is noise. Not noise in the way a trumpet is loud, but in the way a crowd is loud, even if every voice is whispering. Heat is molecules jostling, particles vibrating, everything moving just a little too much to be quiet. And quantum physics? It hates noise. Quantum effects, superposition, entanglement, interference, they require silence. The kind of deep, perfect silence only found in the coldest corners of the cosmos, where particles can spread out like sighs, where possibilities aren't shattered by collisions, where uncertainty can breathe. The closer you get to absolute zero, the more clearly the quantum world begins to emerge. Let's take a journey. You're shrinking now softly, dreamily, until you're smaller than a speck of dust. You find yourself floating near a single atom, chilled to nearly nothing. The temperature is so low that the atom barely vibrates. It exists in a quiet stillness you didn't think was possible. And here, only here, can it show its quantum colors. It spreads, it shimmers, it enters superposition with ease. It entangles with others like dancers, moving in perfect silence. Because there's no heat to ruin the choreography. Now imagine raising the temperature, just a little. The atoms begin to bounce. They jiggle, just slightly, then more, Suddenly, they're bumping into photons, into each other, into the walls of their world. Each bump is a measurement, a collapse, a broken wave function. The quantum ballet stumbles and falls. At room temperature, your ordinary everyday life, the noise is unbearable. For particles, it's like trying to meditate in a mosh pit. There's no chance for subtlety, no stillness to maintain superposition. Everything collapses before it even begins. This is why quantum physicists build refrigerators the size of cars just to cool tiny objects. We're talking fractions of a degree above absolute zero, colder than deep space, colder than Pluto's shadow. And only there, in that coldest of cold, do atoms remember how to be quantum again. It's not that warmth destroys quantum behavior, it just overwhelms it, buries it beneath a flood of interaction. So, if you've been wondering why quantum effects don't rule your morning commute, it's this. Because you're warm. Your breath, your thoughts, your oatmeal, they all exist in a universe that is too busy, too loud, too hot for the quantum dance. But let's not frame temperature as the villain. Warmth is what makes life possible. Without it, your cells wouldn't work, your heart would stall, your neurons would stop firing. Life as we know it requires noise, movement, chaos, the very things that suppress the quantum. There's a trade-off here. The colder you get, the closer you come to quantum purity. But you also leave behind the messy, marvelous thing we call living, emotion, choice, lunch. Still, there's beauty in the edge. Consider Bose-Einstein condensates. They're sometimes called the fifth state of matter, and they only exist near absolute zero. In that cold, atoms stop acting like individuals. They lose their identities and behave as one giant, fuzzy quantum entity. Hundreds of thousands of atoms moving as a single wave function. One big shimmer. It's like a symphony where every instrument merges into one perfect note. This isn't sci-fi, it's real. You can make one in a lab if you're patient, careful, and cold enough. It's another reminder that the rules of the universe haven't disappeared. They're just masked by warmth, by motion, by life. And there's something poetic in that. The quantum world is still here, always has been, but like a ghost in daylight, it's hidden by the warmth of existence. Maybe that's how some parts of yourself work, too. Maybe there are thoughts, soft, subtle, uncertain, that only emerge in stillness. When the day cools, when the noise fades, when everything slows enough for the shimmer to return. Not everything needs to be bright to be real. Some truths, like quantum waves, require quiet. So tonight, you drift through a cold so gentle it doesn't sting, a quiet so pure it doesn't echo, and somewhere, in this imagined chill, you sense it, the rules bending back, the quantum softening back into view. You are not in superposition, you are not entangled, but you are softening, you are quieting, and that's enough. So let the warmth of your body stay, but in your mind, let things cool. Let the particles of your thoughts stop bumping. Let them hover, uncollapsed, unrushed. Let yourself become a gentle wave in a still chamber. And rest. You're resting now in that lovely liminal zone, half breath, half thought, where the world feels distant and your body hums like a gentle machine. Let's stay here a moment and talk about something simple. Size. Not in the way you normally think of it. Not tall versus short. Not whether something fits in a box or a pocket, but in the quantum sense, how scale reshapes the rules. You've learned that quantum effects, superposition, entanglement, wave-particle duality show up beautifully in small things. Electrons, photons, atoms, tiny systems that can be cooled and isolated and coaxed into behaving like shimmering possibilities. But the bigger things get, the more classical they become. The rules tighten, the shimmering fades, the world settles. Why? Well, for one, size multiplies complexity. Let's say you start with a single particle. It has a wave function, a simple equation that describes its probabilities, its maybes. Add a second particle, and now their wave functions combine, multiply. They don't just double, they entangle, interfere, dance. Add a third particle, a fourth, a fifth, and suddenly the number of possible states explodes exponentially. Now take an object the size of a grain of sand. You're looking at something with about a quintillion atoms. That's a 1 followed by 18 zeros. Each atom has its own little quantum state, its own direction it could shimmer. Now imagine trying to track every single possibility. The math breaks. Reality doesn't, of course. Reality just settles. The system becomes so entangled with itself and with the world around it that it quickly decoheres. It falls into something stable, something predictable. That's what big does. It doesn't break quantum physics. It buries it. Another way to think about it is through wavelength. Remember Louis de Broglie, the physicist who said that all matter has a wavelength? The smaller the momentum, the longer the wave. That means tiny particles, slow-moving ones, have long, spread-out wave functions. You can see their interference, their shimmer. But big things, fast-moving things, their wavelengths shrink, compress, so tight they're essentially points. No visible wave, no observable interference, just a sharp blip in space. A baseball, for example, has a wavelength so small it would take a universe-sized double-slit experiment to see its wave behavior. Good luck setting that up in your backyard. That's why you never see a pizza interfere with itself, or a shoe tunnel through a wall. Not because the rules don't apply, but because the effects are unfathomably small. Still, those rules do apply, always. Quantum physics underlies everything. It's the base layer of the universe. The fact that macroscopic objects don't shimmer doesn't mean they aren't quantum. It just means that the quantum weirdness has averaged out, collapsed, dissolved into statistical noise. It's like trying to hear a single violin in the middle of a hurricane. The note is still playing, but good luck picking it out. And yet, physicists keep trying. They've created experiments where increasingly larger objects, clusters of atoms, small mechanical systems are put into quantum states. Superposition, interference, even entanglement. In 2019, a tiny drum big enough to see with the naked eye was cooled to near zero and placed into a quantum superposition of two vibrational states, a drumbeat, both struck and unstruck. Think about that. A thing you could hold in your hand, doing something quantum. For a moment, before the noise crept back in, it proves that the boundary is not fixed. It's not a rule. It's a sliding scale. The bigger you get, the more difficult the quantum becomes, but not impossible. The universe doesn't say, "You're too big for this." It just makes the requirements harder, like asking an elephant to tiptoe across a spider web. Technically doable. Practically, no. But maybe one day, we'll find a way. We might build quantum machines the size of teacups, or see interference patterns in bacteria, or store memories in quantum states that span thousands of molecules. Every year, the line between quantum and classical is pushed further. Still, even if we never fully see it in our ordinary lives, it's comforting to know the weirdness never really left. The macroscopic world, the one with chairs and cereal and gravity, is not separate from the quantum. It's just the result of billions upon billions of collapses, decoherences, interactions, all smoothed out into something stable. You're made from those processes. Your heartbeat is a classical echo of quantum rhythms. Your thoughts, your emotions, your breath, all emerge from the microscopic dance of possibility and collapse. And that makes you not just part of the universe, but part of its deepest language. So as you lie here, in a body full of trillions of atoms, each obeying laws too small to notice, remember this. You are the sum total of countless quantum whispers. You may feel solid, predictable, classical, but inside you, always, the shimmer remains. You're far from where you began now. The world of coffee cups and calendars has faded. What's left is soft, almost transparent, just the breath of ideas, floating on the edge of sleep. It's the perfect moment to ask something gentle but serious. Can you measure something without touching it? Can you observe the universe without disturbing it? In quantum mechanics, this is the ultimate paradox, because the act of measurement isn't passive. It's not like checking the time or glancing at the moon. It's invasive. It changes what's being measured. Let's go back to our old friend, the electron. You want to know where it is. Simple question. But to see it, you have to bounce something off it like a photon. That's the quantum equivalent of tapping someone on the shoulder with a tennis racket. Suddenly, your electron is no longer floating gently in its probabilistic cloud. Now it's been knocked, moved, changed. The very act of asking, "Where are you?" alters the answer. This is known as the observer effect. And it's not just a technical annoyance, it's a foundational truth. In the quantum world, the line between observer and observed vanishes. You can't look without becoming part of the system. And that raises a wonderfully unsettling question. What is measurement, really? In classical physics, measurement is simple. You weigh a rock, you check a temperature, you count marbles. The system doesn't care if you're watching. But in quantum mechanics, observation is an interaction, a disturbance, an entanglement. When you measure a particle's position, you lose information about its momentum. When you check its spin, you collapse all the other states it might have occupied. The act of observing forces the system to make a choice, as if the universe is saying, "Fine, you want an answer? Here's one, but now all the other questions are off the table." This is captured beautifully by Heisenberg's uncertainty principle. It says, the more precisely you know one property, like position, the less precisely you can know another, like momentum. Not because your tools are clumsy, but because reality itself doesn't allow both to be sharply defined. The world isn't fuzzy because you're bad at measuring. It's fuzzy because fuzziness is built in. Now here's where it gets even more dreamlike. There are experiments, real ones, where particles are measured without being directly touched. This is called weak measurement, and it's a strange and subtle dance. You extract a little information, just a whisper, without collapsing the wave function entirely. It's like listening to a conversation through a pillow. You don't hear everything, but you hear enough. Other setups use something called quantum non-demolition measurement, a way to measure one property repeatedly without destroying the system. These methods are delicate, difficult, but they suggest that, maybe not always, but sometimes you can learn without breaking. Still, the core truth remains. In most quantum situations, to measure is to change. And that's not just a scientific detail, that's a life detail. Because we do this to each other all the time, don't we? We observe someone, and by observing, we alter them. We ask questions, and the answers shift in response to our tone, our timing, our gaze. You're not a neutral observer in anyone's life. You leave fingerprints just by being present. Maybe that's not a flaw. Maybe it's a gentle reminder that presence matters, that attention is powerful, that to see something fully is to participate in its becoming. So, next time you glance at a raindrop, a friend, a flower blooming in the dark, remember, you are not just noticing, you are witnessing into being. Let's stretch this idea one step further. There's a school of thought that says measurement is not just a moment but a process, that it's not when the detector beeps, but when the result becomes irreversible, recorded, remembered, shared. Which leads us to a strange realization. Until a measurement becomes part of the world, a ripple in reality, a note in the universal memory, it might not count. A particle may pass through a device, interact with atoms, leave a trace. But if no one ever sees that trace, if the data is lost, if the system forgets was it measured, it sounds like metaphysics, but it's science. And perhaps also life. How many moments do we experience that we never fully measure? Feelings that drift by, uncollapsed, ideas that fade before we notice, people we brush past without truly seeing. The quantum world seems to whisper, pay attention, but gently. Look, but don't always grab. Let some things shimmer. So, tonight, as your thoughts float freely, let this idea settle in. Measurement is real, but it's also a choice. You don't have to observe everything. You don't have to name every feeling or define every part of your life. Some things are better left a little uncertain, a little unmeasured, because in that uncertainty, beauty lingers. And maybe, just maybe, your mind quiet now, unbothered, is a kind of quantum system too. Left unmeasured, it can rest, drift, superpose, and collapse softly into sleep. Sleep is brushing your fingertips now. Thought is slowing into rhythm. But before you fully cross into the dark, just before the final collapse of waking, we must visit a quiet idea. Time. We treat time like a river, always flowing, always forward. But down in the quantum realm, time doesn't behave the way you expect. In fact, time might not exist at all, at least, not in the way your clocks suggest. Let's pause everything. Sit beside a particle in a cold vacuum. Nothing is happening, or is it? In quantum mechanics, nothing is never truly nothing. Even in stillness, particles jitter, fields ripple, virtual particles pop into existence, then vanish like hiccups in space-time. And through all this, time ticks, or seems to. But how do particles experience time? Here's a twist. Many quantum systems don't seem to care about it. The equations that govern them, like the Schrödinger equation, are time, symmetric. That means they don't mind whether time goes forward or backward. Yes, backward. A quantum wave function evolves just fine if you reverse the flow of time. There's no preferred direction baked into the math. It's only when you measure something collapse the wave function that a clear before and after appears. And that collapse, that's irreversible. That's what gives you the arrow of time. This idea is quietly radical. You see, in classical physics, time marches on because entropy increases. Systems become more disordered. Ice melts, smoke disperses. That's the thermodynamic arrow. But in quantum mechanics, entropy doesn't build in the same neat way until you introduce an observer, until someone looks. Suddenly, the system has to commit. And that commitment, this happened, not that creates a split, a direction, a one-way street. Time, it seems, is not a river, it's a story, a sequence of quantum choices written down by interaction, memory, and irreversibility. Now let's get stranger. Some interpretations of quantum theory, like the two-state vector formalism, propose that particles don't just have a past guiding them, they also have a future reaching backward, as if what will happen influences what has happened. Yes, you heard that right. Retrocausality. Future events shaping present ones. Not in a science fiction sense, but in a quiet, statistical way. No paradoxes. No phone calls to your past self. Just a whisper in the equations that maybe the universe is more interconnected than you think. You may find that absurd, or beautiful, or both. Let's go deeper still. In some quantum gravity theories, especially ones that try to unify the quantum world with general relativity, time disappears entirely. The equations describe a timeless landscape, a block universe where every moment exists simultaneously. No past, no future, just now, everywhere. In this picture, what you experience as the passage of time is an illusion born from consciousness stepping through one slice of the whole, like flipping through the pages of a book, one by one, even though the entire story already exists. But why would the universe work this way? No one knows. Time is the one thing you experience constantly, but understand least. It feels solid, intuitive, but when you try to define it, to break it into quantum terms, it slips through your fingers. Einstein showed us that time is relative, stretchable, malleable, different depending on where you are and how fast you're moving. Quantum physics shows us that time may not be fundamental at all, that it could emerge from deeper, stranger rules we haven't yet named. So how do you live in a universe where time might be optional? You do what you've always done. You breathe. You move. You feel. You mark the moments not with math, but with memory, with music, with story. You experience time as change, heartbeat to heartbeat, thought to thought. And maybe that's enough, because whether time is real or emergent, linear or looped, one thing remains. You live through it. You are it. Your life is the only clock that matters. And right now, the hour is rest. So here's a thought to carry into your dream. What if your memories aren't stored in the past, but are waiting in the future, reaching back to you? What if time, instead of a line, is a thread being woven from both ends, your choices pulling from what was and also from what could be. There's a line from a physicist. Time is what prevents everything from happening at once. But maybe, in the soft quantum truth, everything is happening at once, and you're just moving through it, gently, frame by frame. So now, release the clock. Let the ticking fall silent. Let time pause, or bend, or vanish altogether. Because here, in this breath, in this moment, there is no before, no after, only the stillness between, and the shimmer of sleep, waiting. You've left the tick of clocks behind now. You float where seconds stretch and collapse. But as you linger in this stillness, a question emerges, soft and electric. What about you? Not your body, not your breath, but your mind. In all this quantum talk, particles, waves, time, there's been a shadow idea following close behind. It's something ancient philosophers, spiritual seekers, and tired graduate students have all asked. What role does consciousness play in reality? It's not an idle question, because if measuring collapses the wave function, and measurement requires an observer, then what is the observer? You? A machine? A photon? The idea has haunted physics for a century. Some interpretations, like the Copenhagen interpretation, leave it vague. The wave function collapses upon observation, sure, but they don't say who or what qualifies as an observer, and some physicists couldn't leave that ambiguity alone. Enter the consciousness causes collapse hypothesis. It suggests that wave functions remain in superposition until observed by a conscious mind. That awareness, your awareness, is what forces the universe to make a choice. In that view, you're not just watching reality, you're constructing it. But let's slow down. That sounds profound, yes, but also suspiciously human-centric. Like the universe is just waiting for you to open your eyelids before it gets to work. Still, people like Wigner, von Neumann, and even Schrödinger toyed with the idea. Not because they were mystics, but because quantum theory keeps hinting that the act of observation changes the world. And if no one's looking, what does real even mean? But this idea that consciousness causes collapse has fallen out of favor with most physicists. Not because it's proven wrong, but because it's inconvenient. It invites more questions than answers. What counts as consciousness? A human? A chimp? A spider? A slime mold? If no one's around, does the universe stay uncollapsed? It's easier for science to let go of the mystery. Newer interpretations, like decoherence theory, suggest that collapse isn't tied to minds at all. It's about interaction. When a quantum system bumps into its environment, the superposition falls apart not because a brain noticed, but because the system became entangled with the world. In this view, measurement is just math. No mind required. But here's the thing. We still don't know. No interpretation is universally accepted. The mystery lingers, which leaves space for imagination, for wonder. What if consciousness is entangled with the cosmos? Not in a mystical, incense-burning kind of way, but in a scientific way. What if minds don't just observe the universe, but arise from it, built from the same quantum stuff that shimmers and collapses? Some physicists and philosophers believe that consciousness is an emergent quantum phenomenon, that your awareness might stem from quantum processes in your brain, tiny tubules inside your neurons, vibrating in harmony with quantum rhythms, creating the warm illusion of a self. It's speculative, controversial, but it's not nonsense. There are serious researchers exploring quantum consciousness as a framework, not because it's poetic, but because classical models of the brain still leave gaps. No one fully understands how matter produces mind. And quantum mechanics, it's the science of possibility, of connection, of subtle effects that ripple across space and time. Sounds like a good match. Still, we tread carefully. We don't need to prove that consciousness collapses wave functions to feel awe. It's enough to admit that we don't know where the line is, that we don't fully understand what it means to observe. And maybe, just maybe, that's the point. Maybe you're not here to collapse reality. Maybe you're here to witness it, to marvel at it, to feel it echo inside you. And there's something quantum about that too, because witnessing isn't passive, it's participatory. It creates story, it creates meaning. It weaves together what is with, what it feels like to be. You are not separate from the universe. You are a wave, collapsed into awareness. The physicist John Wheeler once said, "We are participants in bringing into being not only the near and here, but the far away and long ago." It sounds poetic, but in quantum mechanics, poetry sometimes gets close to truth. So lie still now, conscious observer. Whether or not your mind is collapsing wave functions, whether or not you're the final measurement the universe has been waiting for, you're here, aware, drifting, held, and the world is shimmering, still partly undecided, waiting for nothing in particular, only presence. And tonight, yours is enough. You're suspended in a soft question now, no longer needing answers. The world has become quiet, smooth, uncollapsed, and yet, somewhere, faintly, a door opens in your mind. What if every possibility happened? Not metaphorically, not as a what if you carry in your heart, but really truly every possibility. Welcome to the many worlds interpretation. It's not a fantasy. It's one of the most serious contenders in the race to understand quantum mechanics. And though it may sound wild, it actually solves a deep problem. You've heard the story. A quantum particle exists in superposition many states at once until it's measured. Then, poof, the wave function collapses. The particle chooses. One version becomes real, the others vanish. But why should they vanish? That's the question Hugh Everett asked in 1957. His answer? They don't. The wave function never collapses. Instead, every possible outcome happens, each in its own separate branch of reality. Every time you make a measurement, the universe splits not like a dramatic explosion, but a quiet duplication. In one world, the particle goes left. In another, it goes right. And yes, that includes you. There's a version of you that sees the electron hit the left detector, another that sees it hit the right. Both are real, both exist, neither knows about the other. It's not that the universe branches. It already includes all branches. You just find yourself on one particular path, reading this one particular sentence, drifting into this one particular dream. You don't watch the universe collapse. You ride the branch you're on. This idea sounds outrageous, but in some ways, it's the most elegant solution of all. It removes the need for special collapse rules. It keeps the equations pure. The math flows smoothly, without any awkward measurement hiccup. And if you're wondering, yes, many physicists take this seriously. Because the many worlds interpretation doesn't add anything strange to the theory. It simply follows the math to its most logical, if unsettling, conclusion. It says, the universe is not singular. It is a superstructure of all possible realities, humming together, separated only by decoherence. You can't cross from one to another. But every time a quantum choice happens, every time a particle could go A or B, both paths exist, and each leads to a world, a multiverse. But unlike the multiverse of science fiction, with wild portals and alien physics, this one is quiet, smooth. The laws don't change, just the outcomes, just the arrangements. So right now, there may be a version of you brushing your teeth, another staring at the ceiling, another asleep already. A million tiny splinters of identity, each equally real, equally unaware of the others. And if that makes you dizzy, good. It should, because it changes the way you think about choice. In a many worlds universe, every choice happens. Every coin flip lands both ways. Every fork in the road is taken by some version of you. But here's the twist. You only experience one. Your identity rides a single branch. You don't remember the others. You don't feel them. They become background static, mathematically real, but emotionally invisible. So what does this mean for your life? Does it make your choices meaningless? Not at all. In fact, it gives them infinite texture. Each decision you make is a way of carving through the space of all possible outcomes, a way of saying, this is the path I'm taking, not because the others don't exist, but because this one is yours. You are, in this view, a thread through a vast tapestry woven through infinite options, anchored only by attention. And maybe that's what consciousness really is. A lens that rides one reality, while others flicker silently in parallel. Now, let's step back. There's no way to prove many worlds right now. It makes predictions identical to other interpretations. You can't test the invisible branches. Not yet. Maybe never. But still, the idea remains, whispering beneath your every moment. There are other versions of you. Not better, not worse, just different. Versions where you said yes, where you said nothing, where you stayed, or left, or wandered. And maybe that thought is comforting, because it means that all your unlived lives are lived somewhere. All your lost futures, all your what-ifs, all your mistakes and miracles, they exist. Not in fantasy, in physics. You don't need to hold on to them. You don't need to fix or regret. Because here on this branch, you are exactly where you're supposed to be. Not because it's better, because it's real. And as you drift now, deeper into sleep, let that reality settle around you like a blanket. Let the other paths fade, not with sorrow, but with quiet gratitude. They are taken care of, lived by someone who is also you. You don't need to split. You just need to rest. In this world, on this branch, under this sky, and trust that somewhere, the universe continues to shimmer possibility, unfolding forever, in silence. Now you're floating in a world with many versions of itself, each branch quiet, each possibility tucked neatly into its own silence. And yet here you are, still, breathing, collapsed into one clear moment. But beyond the metaphors and mysteries, let's return to something more tangible, more technical. Let's open the fridge, because inside it, cold, humming, shielded from the noisy world, is one of the most delicate machines ever imagined. A quantum computer. Unlike the laptop or phone you're used to, which crunches numbers using bits, zeros and ones, on or off quantum computers use qubits. Qubits don't choose 0 or 1. They exist in superposition. They are both, until they aren't. Let's compare. A classical bit is like a light switch up or down. A qubit is like a spinning coin. But here's the trick. The coin isn't just spinning, it's shimmering through all possible angles, influenced by how you prepare it, entangle it, and finally, measure it. Now imagine 2 qubits. 3. 10. With 10 qubits, you can represent over 1,000 states simultaneously. 20 qubits, over 1,000,000. Quantum computers don't just process more, they process differently. They explore a landscape of probabilities. They can perform certain tasks, like factoring large numbers, simulating quantum systems, or solving optimization problems faster than any classical machine ever could. But why are we talking about this now, here, in the gentle dark? Because a quantum computer is not just a machine, it's a metaphor. It's a physical embodiment of all the rules we've been drifting through in this quiet journey. Superposition, entanglement, decoherence. It's the closest we've come to making quantum weirdness useful. And to keep that weirdness alive, quantum computers must be cold, icy cold, colder than space, near absolute zero. Why? Because as you now know, quantum states are fragile. A warm environment means particles jostle, superpositions collapse, entanglements die. To keep qubits in their shimmering maybe state, you must isolate them, protect them, let them float in stillness. Some quantum systems use superconducting circuits, loops of current flowing in both directions at once. Others use trapped ions, suspended in place by lasers, vibrating with quantum precision. Still others use photons, or even defects in diamonds, where a missing atom becomes a window into quantum logic. Each approach is different, but they all share a goal: to tame the quantum, to catch it before it collapses, to compute not in single outcomes, but in waves of possibility. And they're not just theory, they exist, they're real. Companies like IBM, Google, and startups scattered across the world are building quantum computers right now. They're not yet better than classical ones, not for most problems, but they are growing, learning, cooling. They are seeds of the quantum world, planted in silicon. And someday, they may change everything, not just in science or technology, but in how we understand thought, memory, creativity. Because quantum systems don't move step by step. They don't think in lines, they think in clouds. And maybe that's closer to how you think. Maybe your mind is less like a calculator and more like a quantum processor holding many thoughts at once, many feelings, uncollapsed, unresolved, waiting for a moment to decohere into a decision. Sometimes, sleep itself feels like a quantum computation. Your mind drifts through dreams, narratives you never scripted, combinations you never consciously chose, and in the morning you awaken with clarity, as if the wave function of confusion finally collapsed into insight. Quantum computers are still in their infancy. They make mistakes, their qubits are noisy, their coherence times how long they stay quantum are short. They need error correction, shielding, patience. But so do you. Your thoughts don't always hold still. Your feelings shimmer. Your beliefs entangle with your memories. You collapse, then expand again. You're never just one state. You're a probability field in motion. And that's okay. That's human. That's quantum. So tonight, as you rest, imagine your thoughts cooling. Let the noise drop. Let your mind settle into coherence. Not the mechanical kind, the peaceful kind, the kind where all the tangled possibilities of the day finally hush and you drift into the solution space. Sleep, after all, is not the end of thinking. It's parallel processing. It's quantum restoration. It's where your brain explores options without needing to decide. So rest like a qubit entangled with the sky, coherent with silence, suspended in superposition. And trust that in the morning, when the world warms again, you'll collapse gently into just the right version of you. So here we are, past the metaphors, past the shimmer, past the cat, the clock, the coin that spins and doesn't land. And yet, a deeper question still hums beneath everything. Where does quantum end and classical begin? Where, exactly, is the great wall between the weird and the familiar? You'd think, by now, we'd know. We've spent a century peeking into atoms, coaxing particles into mischief, building computers that compute without choosing. And yet, no one can point to the precise boundary. There's no switch, no sign that says, now entering classical reality. Instead, what we see is a gradient, a soft curve from the whisper of uncertainty to the roar of stability. And the transition, it happens not with rules, but with pressure, with scale, with entanglement and environment. Let's revisit a metaphor, because sleep likes stories more than equations. Imagine reality as a vast ocean. The quantum world is the deep, quiet, dark, unknowable. The classical world, it's the shore, clear, visible, tangible. Between them lies the surf, the wall, and this surf isn't still. It changes depending on the conditions, temperature, size, isolation, measurement. You can stand on the sand and dip a toe into quantum strangeness, or dive deep and lose all sense of up and down. But there's no clear place where the tide turns to land. Physicists call this the quantum classical transition, and they've built entire fields of study trying to explain how classical behavior emerges from quantum rules. Not replaces, emerges. That's key. There is no classical physics without quantum physics. What looks like certainty apples falling, marbles rolling, is the sum of so many quantum events decohering all at once that the weirdness gets washed out. Like noise averaging into silence. Like chaos folding into form. The equations still apply. Always. They just become effectively invisible when enough particles get involved. You might have heard of a concept called macroscopic realism. It's the belief that large objects exist in definite states, even when not observed. That your couch doesn't flicker between here and not here while you're in the kitchen. Quantum physics quietly disagrees. It says, if you could isolate your couch from the environment perfectly, no photons, no air, no vibrations, it too could enter superposition, could be in two places at once, could interfere with itself, could shimmer, but the requirements are absurd. The time window would be impossibly short, and the slightest glance a single rogue particle would snap it back to classicality. So, instead, we call it real, because for all practical purposes, it is. But here's something comforting. Even though the quantum wall hides the weirdness, it never removes it. The world you know, your bed, your room, your memories, is made from uncertainty. Just very, very well-behaved uncertainty. And every once in a while, the wall flickers. A quantum effect escapes. A molecule interferes with itself. A circuit entangles. A system stays coherent longer than expected. And when it does, it reminds us that the classical world is not a separate kingdom, it's just the quantum world in disguise. So what determines when that disguise drops? There are several theories. One is environment-induced decoherence, which you already know. The more something interacts, the faster its superposition collapses. Another is coarse-graining, the idea that when we look at large systems, we lose the fine-grained detail. We average out the quantum messiness into something classical-looking. And some suggest that even gravity might play a role. That mass itself could resist quantum behavior. This is speculative, but fascinating, that perhaps gravity, the last great mystery of physics, is the thing that holds the wall in place. We don't know, but what we do know is this. The classical world is a mirage of agreement, a consensus formed by billions of particles interacting just enough to pretend everything is stable. Straight lines, definite outcomes, linear time. It's a charade that holds just long enough for consciousness to form, for you to live, for you to sleep. So tonight, you're lying not in a classical world, but in a fragile symphony of entangled particles pretending to be solid, pretending to be warm, pretending to be certain. And what holds that illusion together? Scale, interaction, time, memory, but most of all you. Because here's the twist. The wall between quantum and classical isn't just a physical transition, it's a perspective. From far enough away, particles blur into objects, uncertainties smooth into facts. The closer you zoom, the more you see the cracks, the shimmer, the possibility. It's all there, always. So as your thoughts settle tonight, rest in the knowledge that the weirdness never left. It didn't go away, it simply became cooperative. It agreed to behave so you could brush your teeth, hug a friend, watch the rain. There is no wall, not really. Only a slow, beautiful curve from maybe to yes. And here, at the edge of yes, you sleep. You're deep now where dreams blur with memory, and your breath has become the only rhythm left. The quantum world has quieted too, not gone just rearranged, softened. But how? That's tonight's question. How does the classical world emerge from quantum chaos? How does weird become ordinary? The answer, many physicists whisper, especially in the halls where equations echo and chalk dust drifts, is a concept called emergence. Emergence is when simple rules, layered and looped, give rise to complex behavior that looks nothing like the rules themselves. Think of it this way. No single water molecule knows what a wave is, but put enough together and the wave appears. That's emergence. The classical world, your breakfast, your heartbeat, your toothbrush is a wave. And the molecules? They're humming quietly underneath, following rules that have nothing to do with eggs, arteries, or mint-flavored foam. So what exactly is emerging? Let's make it vivid. You're looking at a chair. It's red. It's solid. It stays where you left it. But zoom in, and the atoms in that chair aren't still. They vibrate. Their electrons shimmer in fuzzy clouds. Even deeper, the protons and neutrons inside each atom are made of quarks, held together by gluons, flickering in and out of virtual reality. None of those particles are red. None are solid. None even stay in one place. And yet, the chair, its color, its comfort, its reluctant squeak, they emerge from the dance below. This isn't just poetic. It's structural. It's mathematical. Systems of particles, following quantum laws, naturally form larger systems molecules, lattices, crystals that begin to exhibit collective behavior. At some point, that behavior stops looking quantum. It starts looking classical. That's emergence, the point where the sum becomes more than its parts, not in spite of their weirdness, but because of it. One of the most beautiful examples, superconductivity. At low temperatures, certain materials allow electricity to flow without resistance, not because the electrons are behaving normally, but because they're behaving together, in sync, in perfect quantum alignment. They form what's called a macroscopic quantum state, a single wave function that describes millions of particles acting as one. This shouldn't happen, but it does, because the emergent behavior of these systems doesn't just obey the quantum rules, it transcends them. Another example? Life. You are not just a collection of particles. You are emergent. Your heartbeat, your laughter, your memories of that one afternoon in 5th grade, they rise out of trillions of interactions between molecules, cells, synapses. There is no laughter particle, but here you are, laughing. There is no thought quark, but here you are, thinking. Emergence is why we can live in a quantum world and not notice. It's the universe's way of smoothing out the chaos, of creating layers, each with its own rules, each dependent on the last, but not reducible to it. And that matters, because it means we don't have to choose between quantum and classical, between weird and real. One rises from the other, like melody from notes, like temperature from motion, like sleep from quiet repetition. It also means that reality has texture. The closer you look, the stranger it gets. But step back, and it becomes something you can hold, sit on, trust. That trust? It's emergent too. It's the result of billions of particles whispering, yes, we will behave today. And somehow, through that agreement, a stable world is born, but not always. Sometimes, emergence breaks down. In certain materials, systems go rogue. They display quantum criticality, where even macroscopic properties start to shimmer, behave unpredictably, defy classical logic. At these edges, the rules leak, and that's where new physics begins. So don't think of emergence as a wall. It's a threshold, a doorway between chaos and structure, and like any good doorway, it swings both ways. We emerged from quantum noise, but maybe, someday, we'll find our way back in. Quantum computing is one way. Brain studies are another. Even ideas about consciousness, yes. Even those may lead us back to the place where everything was uncertain, but everything was possible. So tonight, as you lie in your emergent body, in your emergent bed, under your emergent ceiling, let that comfort you. Reality doesn't have to make sense from the top down. It just has to hold together from the bottom up. And it does. Somehow, with you in it. Let your breath emerge now, from silence. Let your thoughts scatter into smaller and smaller pieces. And when only shimmer remains, you'll know you've arrived. The shimmer has softened into stillness now. Every breath feels like a ripple in a vast, calm sea. You've traveled far from particles that don't commit to the lives they might lead, to the world you know, where things fall, stay, break, heal. But there's one place we haven't quite visited yet. The void between worlds. The place where physics falters, where gravity meets quantum and they refuse to speak to each other. Let's go there now. You've probably heard of Einstein's general relativity, a majestic theory of how matter curves space and tells it how to move. A smooth, continuous field. No jumps, no fuzziness, just elegance. Then there's quantum mechanics. Jittery, discrete, probabilistic. It doesn't care for smoothness. It describes a world where things blink in and out, where uncertainty rules, where probabilities replace precision. Here's the problem. They don't agree. General relativity is perfect for stars, planets, galaxies. Quantum theory is perfect for atoms, particles, fields. But try to apply both at once, say, inside a black hole, or at the birth of the universe, and the math breaks. the fabric of understanding tears. Physicists have spent a century trying to stitch them together. String theory, loop quantum gravity, holographic principles. Every attempt is bold, some are beautiful, none are complete. This failure, this silence at the heart of physics, is oddly humbling. We know so much. We've measured the spin of particles to 10 decimal places. We've mapped the curve of space with satellites. But we still don't know how to describe the quantum nature of space-time itself. Let's make this more vivid. Imagine zooming into the fabric of space, smaller than atoms, smaller than quarks. You reach the Planck scale, a realm so tiny, distance itself might be quantized, granular, not continuous, but made of discrete bits of information. Space, it turns out, might not be smooth at all. It might be pixelated. And time? It might not flow, but occur in jumps, flickers. Some theories suggest that space and time themselves emerge from entanglement. That geometry up, down, near, far is not fundamental. It's woven together by relationships between quantum bits of information. If this sounds like science fiction, that's fair. It's also the leading edge of science. Consider black holes. According to relativity, they are regions where gravity is so intense that space folds in on itself. But quantum mechanics tells us information can't be lost. So, what happens to the information that falls into a black hole? This is known as the black hole information paradox. It's not just an academic puzzle, it's a war between the two foundational pillars of physics. But maybe the answer lies in the shimmer. Some physicists believe that black holes aren't holes at all, but holograms, objects whose contents are encoded on their surfaces. That space inside is an illusion. That the universe itself might be a hologram, built not from position and momentum, but from entanglement patterns. In that view, gravity is not a force, it's an emergent property. Not a thing in itself, but a consequence of quantum relationships. And suddenly, you start to see a pattern. Relativity curves space. Quantum theory weaves it. Emergence bridges them. We just haven't found the full stitching yet. Now, why does this matter here, tonight, while you're drifting towards sleep? Because in the quiet space where gravity and quantum meet is the deepest kind of mystery, the kind that hums under everything, the kind that reminds us we don't have all the answers, not even close. We understand the dance of particles. We've mapped the sky. We've built machines that think. But when it comes to the structure of the universe itself, what time is, what space is, we are still children drawing stars in the sand. And maybe that's a gift, because it means there's still wonder, still mystery, still more to learn, even in an age of smart watches and satellite maps. It also means that your questions, those quiet, aching ones that stir when you lie awake, are not so different from physics. What holds it all together? Where do I end and the world begin? Why do some things feel too big to know? The universe is still figuring that out too. So tonight, as you fall deeper, know that you are resting in a world not fully understood. And that's not frightening. It's freeing, because uncertainty isn't emptiness. It's potential. Even gravity so stable, so grounding might be born from uncertainty. Maybe you are too. Born from not knowing, held by laws still being written, carried by curves you can't yet see. And that, somehow, is enough. So let the silence between gravity and quantum hold you. Let it be the softest pillow. Let the unanswered questions be your lullaby. Because the universe doesn't need to resolve everything right now. It just needs you to rest. By now, you're part of the quiet. You've become it. The breath, the stillness, the space between thoughts. But before this journey ends, there's something you need to hear. Something simple. You are made of quantum mush. Not metaphorically, literally. Your body, this warm, humming self, is built from atoms. Each atom is a floating cloud of probabilities, wrapped around a nucleus that pulses with quantum confusion. Inside that nucleus, protons and neutrons, themselves made of quarks held together by gluons flickering in and out of existence. You are not solid. You are not still. You are a storm of maybes, temporarily pretending to be a person. Let's take a closer look. Start with your hand. Not the image of it, but the thing itself. If you could zoom in past the skin, the cells, the molecules, you'd find something strange, mostly emptiness. Vast, cold space between particles, and in that space, nothing is ever quite in one place. Electrons don't orbit like moons, they hover, smear. They're described by wave functions probability fields that say the electron might be here, or everywhere in between. That uncertainty, it's built in, irreducible, not because we're bad at measuring, because the particles don't have precise locations until we measure. You are made of these things. And yet, you're also brushing your teeth, paying taxes, singing in the car. So what gives? Again, it's emergence. Your brain, your muscles, your voice, they all arise from quantum rules that, when layered, become stable, predictable, classical. But they're still quantum underneath. Your neurons? They fire in part because of quantum tunneling, a particle passing through a barrier it technically shouldn't be able to cross. That's not rare. That's how biology works. Without quantum effects, you wouldn't be alive. Without uncertainty, DNA couldn't replicate. Without entanglement, photosynthesis wouldn't function. Even your memory may rely on quantum coherence. It's being studied. So if you've ever thought, quantum physics feels so far away, stop. It's not. It's you. Every cell in your body carries a map of probabilities. Every breath you take is a negotiation between chance and chemistry. Even your emotions, the way you swell with joy or crumble with grief, are underpinned by particles dancing in ways no one can fully predict. And yes, you might say, that's beautiful, but it's also terrifying, because if everything is quantum mush, where's the you? If your atoms don't know where they are, how do you know who you are? This is where things get subtle. You are not a static object. You are a process, a pattern, a story held together by coherence, like a song played on waves, like a flame flickering but never falling apart. Your identity isn't located in a single particle or place. It emerges from the interaction of trillions of uncertain things. It is the sum of all the shimmer, held briefly, beautifully. And that means something profound. You are both fragile and resilient. Fragile, because at the smallest level, nothing about you is fixed. You're built from probabilities. Nothing guarantees the molecules of your being will hold together from one moment to the next. And yet, you laugh. You remember. You love. You are resilient because the quantum chaos cooperates. It organizes. It plays in harmony long enough to become you. Even sleep, the thing you're falling into now, is built from this process. Waves of electrical activity, neurons shifting states, molecular clocks ticking with quantum precision. Sleep is not separate from physics. It is physics. And maybe that's the secret comfort, that the laws of the universe, the ones that seem cold, indifferent, strange, are the very ones that carry you into rest. So if you ever feel like you're too small, too scattered, too uncertain, remember, you are not alone in your uncertainty. The universe is built from it, and somehow, that uncertainty chose to become you, a pattern of coherence rising from noise, a human imperfect, inconsistent, but real. So lean back. Let your quantum mush soften. Let the particles spin, unmeasured. Let the wave functions spread. Let go of holding yourself together just for tonight. The universe will do it for you. It has every night, since the first moment, and it will keep doing it. Even after you fall asleep, you're barely here now, drifting in that final pause before true sleep. Thoughts dissolve before they finish. Even time has let go of its grip. Perfect. This is where we end. But we won't end with a bang. We'll end with something quieter. A truth so gentle it often goes unnoticed. Quantum effects never disappeared. They just agreed to behave. You've spent this journey, slipping between scales. You've felt the shimmer of superposition, the silent agreement of decoherence, the fragile dance of entanglement, the hush of near absolute zero. You've touched the edges of time. Wondered if your consciousness plays a role? You've tiptoed across branches of the multiverse and peeked into quantum computers humming in their frozen sleep. And now, as we return to the ordinary world, the one where spoons don't teleport and cats don't shimmer, you might be tempted to ask, why? Why don't we see quantum weirdness all the time? And the answer isn't that it's gone or forbidden. It's that it's been folded into order. That shimmer, the maybiness of particles, the undecidedness of the world hasn't left you. It's just been layered, shaped, and silenced into the stable reality you walk through. The coffee mug on your desk? It's still quantum, but every particle in it is tangled up in a web of measurement, of warmth, of interaction. The wave functions have collapsed 1 billion times a second. The possibilities have been filtered into presence. The world you see is what happens when uncertainty agrees to form structure. And that agreement? It's not magic. It's not forced. It's simply what emerges when systems become too crowded to stay quiet. But every now and then, a moment opens, a system cools, an experiment is careful enough, quiet enough, and the shimmer returns. It's not just beautiful, it's constant. You just live in a version of reality where the shimmer has agreed to sit in the background, like the bass line of a song you don't notice until it stops, holding everything in rhythm. So don't let the quiet trick you. Quantum rules are everywhere. They're in the light bouncing off your pillow, in the memory forming behind your eyes, in the breath you just took and the one you forgot to notice. You are not apart from them. You are made of them. And that's maybe the deepest answer to our question. Why don't we see quantum effects in the macroscopic world? Because the macroscopic world is a quantum effect. It's just a well-lit one, a well-measured one, a world where possibility didn't vanish, just made peace with being consistent. Even now, as your awareness slips from this thought to the next, you're experiencing the quiet triumph of the quantum world becoming classical enough for sleep, predictable enough for dreaming, kind enough to let you rest. So here's where I leave you, floating, softly, on a sea of certainty that is anything but certain, wrapped in particles that don't know they're behaving, held together by rules that never stopped being weird, and guided, always, by a universe that never demanded perfection, only participation. So rest now. Let your thoughts decohere. Let your questions go unmeasured. Let your wave function stretch across the sky. You don't need to observe the world tonight. It will shimmer just fine without you. And when you wake, it will still be here, stable, warm, ready. A quiet agreement, signed in silence, held in every atom of your being.